Okay. Thank you, Pim and Malin, for the invitation. So this is a very special thing because once I got the invitation, it reminded me of the COVID days when Life and Andreas were sitting in their drawing rooms, and we were also stuck in our drawing rooms. And those were terrible times, but these talks were like absolutely brilliant. They brought a breath of fresh air, we could connect, and it was really a new world for all of us, attending these meetings. So it's a wonderful opportunity to speak. So we are now everybody back in our offices, so I can see that. But those who are still at home and still looking at this, I generally miss out on this most of the lectures, but I do follow on them on YouTube. Sometimes they're very nice, so I regularly follow them. So uploading them on YouTube is very nice, and I think the slides will also be available on the website very soon. Okay. So today I'll be talking about spectrum of inhomogeneous random graphs. And so first, what I want to talk about is a bit of inhomogeneous random graph. You saw a specific example of that in Clara's talk already. And one aspect I'll be talking about is the spectrum of these graphs. So what I plan to do is, it's a it's a generalization of the classical Erdős-Srény random graph, where for any edge I and j, you put an edge independently with probability Pij. And these Pijs are not homogeneous as you see in Erdős-Srény, but they depend on both I and j, and maybe also some features of the net, these clusters or the pair of vertices you are looking at. So it's a more general structure than the homogeneous, and these kind of models were introduced very long ago by computer scientists and also physicists, but it became very popular in mathematics, especially in the probability literature. I think Bolobas, Janssen, and Riordan were the first one to study this in a more structural way, and nowadays it's a very popular kind of model. So what I'm going to so let me start with the setup of what I call these inhomogeneous Erdős-Srény random graphs. So here is the basic uh, framework. So this framework will go on throughout my lecture. So I have a set of n vertices. So this is the set of vertices which I denote by Vn, and they are indexed by 1 up to n. And each of the vertices will have a certain deterministic weight. So this is a non-negative deterministic weight. I'll briefly mention what happens when I take weights to be random, uh, but I'll come to that later. And there is a connectivity function, which is a bounded continuous function. You could really go outside continuous functions. For example, take almost sure continuous or a bit more general step functions. But we'll work with only, at least for this talk, we'll work with continuous functions, and they are bounded and symmetric. So we'll not consider any directed network. So essentially, what I need is a symmetry in these functions. And I say that two pairs of vertices I and j are connected independently with probability Pij, where Pij has a form which depends on epsilon n, which will be a tuning parameter, and f of wi wj. Now this is my graph. So it's a very general graph, and I'll always assume this epsilon n goes to 0. Otherwise, you'll have to do something else. If you don't let epsilon n go to 0, there are things like that. Now, so first thing I want to know, so this is an abstract description. So are there examples, or what are the good examples which describe such a setup, such an abstract setup? So let us look at some examples. Okay, the first obvious example is that the f has to be 1 and these Pijs are homogeneous. So this is the homogeneous Erdős-Srény where everything is, so the weights don't play any role here. So everything is same. The second example, which Clara was also considering, is the Chung-Lu random graph. So you take a sequence of assume degrees, so di sequence, which is graphical. So there is at least one graph with this degree sequence, and m infinity be the maximum of these degrees, m1 be the average of these degrees, and you define the connectivity function. So fxy is xy minimum 1, and I take weights which are di by the largest degrees, and I choose an epsilon n, which is m infinity square by m1. And then if I write Pij's as I described before, so Pij's was epsilon n f of wi wj. So if I do that, then I get this form. And you can see that di is always less than the maximum degree. So this minimum one is a fake thing. So you can assume that di dj by m1 is your connection probabilities. Now, okay, this is not the usual way you look at Chung-Lu graph, but I'm just putting it in my setting in this form because that's, for me, it's easier to work in this setting. So another example is Noros Ray 2. So this is, again, you start with a DI sequence of given degrees. Your M1 is the average degree, and you take fxy to be 1 minus exponential of xy. So this is a nice bounded continuous function, and you take the weights to be now di by square root of m1, and then you see that you can write the Pij's in this form. And another is what is called generalized random graphs. So let di be again the same kind of thing, and fxy is now again a nice bounded function xy by 1 plus xy, and weights are di by square root of m1. And then again you can form the Pij's in this. So these are four examples. The last one is what I like. It's the simplest of examples where the weights are really just your Riemann points, I by n. So these are just the grid points in your grids. And f is a bounded function from 0, 1 square to 0, 1. And I generally call such functions, when I'm taking here to be 0, 1, such functions to be graphon. So and they are symmetric, so I'll explain what I mean here. But this is the more simpler case of what I described before, but this is an example which sort of gives you the intuition how things work. Okay, so there are multiple more examples I can keep talking about, but what do I want to do with these graphs? So what I want to do with these graphs is look into the spectrum. So so if I take this graph, so I have a matrix which is of an, let's call it adjacency. So this is the adjacency matrix, and so an of ij is distributed as a Bernoulli Pij. And what I'm interested is what happens to the eigenvalues of this matrix. So I can have at most n eigenvalues. So I want to understand the behavior of these eigenvalues as a whole. So now to understand this kind of spectrum, so what happens is there are three methods to understand this. So let's understand the case when f is equal to 1. So this is, everybody knows, it's a simple exercise to see that the expected degree is n minus 1 times epsilon, or epsilon n. You can put an epsilon n, and the variance is also of the order of n minus 1 epsilon n. Now there are three broad cases. You can make more broad cases. For me, these are like, I would like to think of them as the three big ways in which I can look into the spectrum of the random graphs. So one case is when epsilon goes to 0, but the average degree converges to some constant c. And this is what I call the local weak convergence regime, in the sense that these graphs locally look like a tree in most of the cases. And there is a big machinery which was developed in the last, say, 14 years or 15 years, which could be used in studying the spectrum and other properties of these graphs. There is another sub case, which is epsilon is constant, and n epsilon, and hence n epsilon would go to infinity. So this is also quite an interesting case, which is called the Graphon regime. So this is generally, there is a big theory of Graphon theory, which is it was developed by many people in the last 20 years, and that could also be used to study some properties of the spectrum in the dense case. And there is something in between. For example, epsilon goes to 0, but n epsilon goes to infinity instead of a constant. So it could be that n epsilon goes to infinity at least like log n, for example. So this n epsilon could be around log n, or you could have some bounds on this. And these are the cases where you have to resort to different kinds of random matrix theory or ad hoc combinatorics, which comes in. So these are like, so whenever you see a problem in this kind of category, so these are the, you have to first fix your mind and say, okay, where does my problem fall in? And today what I want to show you, okay, that there is a link between all the three cases. So there is a link between the sparse, there is dense, and not very sparse. All of them, there is an interconnection in between everything. What is happening? It's, they are not just completely separate. So that's, I don't have a complete answer, but I'll show you why I believe this. Okay, so let's look into some simulations. So here is the adjacency matrix of an Erdős-Rényi. So this is an homogeneous Erdős-Rényi random graph with vertices, n vertices and epsilon. And as you can see, my n is large, 2000, and epsilon is small. So this is on the regime n epsilon goes to infinity kind of a thing. And here you see a very classically, if you scale the eigenvalues of an, then, so if you scale it like square root of n epsilon, uh, then you see the classical Wigner's semicircular law. So this is the picture of Wigner's semicircular law, uh, and the density looks on -2 and +2 as this. And there is a small factor. So you can see the largest eigenvalue is kind of out there, which is sticking out of the rest of the eigenvalues. And this is very important in applications because uh, whenever you are trying to detect communities or in community detection problems, so these outliers are quite important and challenging to understand, and they carry lots of information. So if you want to understand more complicated features, so you have to understand what are the, which eigenvalues kind of stick out of the bulk or majority, which kind of things which stick out of the majority. So let us see a bit more complicated function. For example, here the fxy, okay, so here the fxy is square root of xy minimum 1. And the weights are, as usual, just the usual weights w of I by n. And again, I'm in the case when n epsilon goes to infinity. So in this case also, now the picture kind of changes. You can see that the peak kind of around 0 is, it increases around 0, but still you see there is just one outlier which is there. And okay, so in this talk, we'll not be interested in this outlier. We'll be mostly interested in what is the shape of this. So how can you predict, or how can you write down an explicit density for uh, such a such a uh, such a curve? So here is an example where it's a bit more with sort of an example with two communities. So you don't need to look into like what the form is, but it's a form where you have that there are two communities and there are not too many connections between each of the communities. And here you can see there are like two eigenvalues which are sticking out of the bulk, indicating that there are two communities there, and the rest of the eigenvalues are concentrated around this region. And this is a typical example of the stochastic block model, which is variously used in different uh, statistics. Okay, so what's our first result? So we are again in the same setup. So we'll state a result first for the dense and the intermediate case together, in a sense that you can mostly in the intermediate case, but I'm adding this condition because without this condition I would need to center my adjacency matrix. So now, okay, that's an additional simplification I'm doing here. So I could state my results without this condition also. So what is the main assumption apart from the setup I initially said? So I'm in the case when the average degree kind of grows to infinity. And if I look at the empirical distribution of the weights, so these are the weights, I'm putting mass 1 by n at each of them, then it should converge to mu of W. So another way of looking at this thing is, so you have your vertex set, choose one vertex uniformly at random and look at its weight. And that should converge to some random weight. And that weight measure is given by this mu W. Now, this mu W plays a crucial role in the description of my limiting measures. And so what one can say is that if I look at the empirical spectral distribution, which is defined by Penn here, that if I look at the empirical distribution, that is, I look at the scaled matrix. So this is an by square root of n epsilon. I have my eigenvalues. I put mass 1 by n on each of them. Then the empirical spectral distribution converges to a measure mu f. And this mu f is compactly supported, and it's a symmetric measure, and the convergence is weakly in probability. So weak comes from the weak convergence of measures, but there is a randomness from the graph itself. So in randomness of the graph, it's in probability. Now, okay, then you can say that, okay, you're not saying much about this function. You're just saying that, okay, mu f is a compactly supported symmetric measure. And you started saying that, okay, you will say something about determining this graph. Now, I'll come to that. So I'll come to the description in a while, more details about what we know about mu f. Indeed, we know a lot about mu f. And if you give me an f, if you give me this weights, I can reconstruct the measure. So I'll be able to tell you how this measure mu f looks like. But first, I want to also discuss about the sparse setting, just to make a comparison on what happens. So PIJs, so you can, so I'm putting n epsilon is equal to alpha. So here, like I can, so this was epsilon, and so I can, so this is like alpha in this case, sparse setting where alpha belongs to some parameter 0 infinity. Now let us look into these graphs. So the first example is the homogeneous case when f is 1. And you see it almost looks like the semicircular law. So here is a sort of semicircular law hidden there. And there is a spike which indicates there is a mass at uh, quite a bit of atom around 0. And this is not much in the sense that alpha is 5. So you should think of here, just to remind what was the connection probability. So Pij is, so alpha by n, for example, here. And alpha is 5 here. And this is an example where Pijs are, if you recall, so it's epsilon of Wi, Wj, where f is of the form xy minimum 1. And you see there is a nice bimodal kind of a picture with the atoms around. So there are these spikes or these atoms, which was, by the way, completely missing when we are in the dense case or the intermediate case. So these spikes appear there. Now, the most interesting part of the simulation, I want to show it because I want to name these people, because these Bauer and Golinelli were the two big names who came out with all the simulations in the homogeneous Erdős-Rényi, sparse homogeneous Erdős-Rényi, and they pointed out beautiful things about this graph. And here are some pictures when alpha is less than 1. So you see alpha is kind of 0.8. So this is the 0.8 case. This is 1. This is 1.2. This is 2. So the transition from 0.8 to 2 is quite dramatic in the sense that at 0.8 you already see all these huge spikes of atoms in a way. So these are huge spikes. And already you haven't crossed 1. So 1 should be the critical, because we know at the Shreni at alpha 1 the tree becomes infinite, and alpha less than 1 the tree is finite. So there is a transition in the geometry at alpha equal to 1. But already at alpha equals to 2 you see that things start becoming quite nicer. And already at alpha 5 you see a structure which is quite smooth, and the atoms are quite less. There are some atoms, but it becomes less. So this is kind of what interested us. So there is a lot. I'll talk about the literature. There is a big uh, chunk of work around these areas. But what interested us is how close does this picture get to the semicircular law? For example, this picture get to the semicircular law as alpha increases. Can we already say around alpha is equal to 10 that you are like a very close perturbation of the semicircular law? Now, okay, this is not apparently immediately clear. So first, what I want to state is a result to which, although we uh, credit to us, but it's a much a general result. I'll tell about the literature. So so we are in the same setting. Epsilon goes to 0, and n epsilon now goes to some alpha, and the weight of an uniformly chosen vertex converges to this mu w. And so what I say is there is a symmetric probability measure which depends on f, my connectivity function, and also alpha, such that the empirical spectral distribution, if I scale it again by square root n epsilon, converges to mu f alpha. Now here, the measures are not really compactly supported, so I don't use the word compactly supported anymore. And I don't give you any further information because that comes later in the talk. So I'll talk more about these when I get to the next part of the talk. But what I already will see from, so that's the main crux of the rest of the talk, is that these measures are very close to the previous dense case. When alpha grows, alpha becomes large. But as I said, alpha equals to 2, alpha equals to 5. These are not really alpha large. So if you see alpha 10, you don't say alpha is going to infinity. So in a sense, so this is not really uh, uh, I wouldn't be satisfied with this result in the way I want to describe it yet. But this is sort of the first step in which I want to head and see how it goes. But the ideal would be that I have a metric, maybe a Kolmogorov metric or a Kolmogorov-Smirnov or a Wasserstein distance or any nice distance, and I want to show that if I look at the distance between the limiting measure, which comes in the sparse case, so this comes in the sparse case, and this is, sorry, there should be an F here. So this is the dense case. So what is the optimal rate between the sparse and the dense case? So that's my, okay, that's the possible target to achieve. I'll not uh, achieve this. Let me just disappoint my those who are listening here that I'll not be able to achieve this, but at least I'll show you that how far we could go. Okay, some literature. This is I apologize those who are experts in this area that it's there is a vast majority of work. I have tried to pick up some works which are kind of closely related to what I am doing, but there is a huge amount of literature. And so one of the things is that when you look at the dense and intermediate setting, you are more in the, as I said, you have to use some of the classical random matrix techniques, and these were recently introduced also by when dealing with finer properties of the eigenvalues, by Ajanki, Erdos, and Kruger in 2017, and there was a huge paper in 2019. So then Easy started looking into generalized Wigner matrix with variance profile and gave a very nice description of the moments. We also in this paper with Arijit, Frank den Hollander, and Mateus Vergara came up with a form which was exactly same as, so these were like just the papers were 1 month apart. We also came up with a form which is similar to what Easy had. And then we extended also a Laplacian matrix with the general variance profile in this paper with Anirban Chatterjee. And and so the largest eigenvalue is very interesting, which I'll not talk about, but those who are interested, they can have a look into these papers by Florence Denia Georges, Charles Bordenave, and Antti Knowles in 2020. So, and there is a recent work by Johannes Dokates and Antti Knowles in 2021, which is also very, very interesting in the sparse setting when n alpha goes. So as I said, the biggest credit, in my opinion, goes to these two physicists like Bauer and Golinelli, because they had some fantastic approximations and results, or also the simulations which initiated this study. Then there is this paper which we'll refer today later by Korunzi, Shervina, and Vengrovsky in 2004. And later, like the theory of local weak convergence was very successfully implemented by Charles Bordenave and Marc Lelage in 2010. And closely related, as we want expansions or how alpha increases, this was also studied by Jung and Lee and Nathaniel Enriquez and Menard in 2013. And largest eigenvalue in the sparse setting is much more difficult. It was studied in this paper by Benaik, Georges, Bordenave, Knowles. There are many fine properties still to be derived. Mu F alpha will turn out to be a very complicated measure. Uh, so Bordenave, Lelage, Sales studied the atoms of these measures. Bordenave, Virag, Sen studied absolute continuity. Coste and Sully's kind of, so they studied emergence of certain more critical states in these atoms, and Arras and Bortunava studied absolute continuity in a more general setting. So a good place to look into these 0-1 matrices is a nice review paper by Alice Guionnet, which is kind of called the Bernoulli random matrices. It has a very comprehensive survey about these matrices, especially in the homogeneous case. So this is just to give you an idea on what the literature looks like. Okay, so if you have any questions till now, because then I'll go to the next part of the talk where I describe the properties of mu f. Okay. Okay, so maybe I continue. Okay. Uh, so so let me go to the dense setting where we have this mu f, and uh, so I want to state some nice properties of this mu f. The first property I want to state is that, so if you take that f is bounded away from 0, then again, so I keep forgetting this f. So mu f is absolutely continuous with respect to Lebesgue measure. Now, okay, how do you show Lebesgue measure? So, so what we in fact showed in a more general case, so these measures, uh, mu f, so if you take out a bit of, because you're bounded away from 0, you can take a bit of chunk out of these f and look at a small perturbation of these measures. Now, what you can show is that mu f is a free additive. So this is a free convolution. So free additive convolution with a semicircular law with certain variance, which depends on alpha. So this is a semicircular law with a different variance. And this immediately gives the result, because semicircular law in the non-commutative world acts like a Gaussian. So what you know is that if you have a random variable say x is a random variable, and you can write it as y plus an independent sum of a normal 0 sigma square, then you immediately know that x is absolutely continuous, because this normal is smoothing out your other random variable y. And the same thing happens when you are sort of looking into the non-commutative space where the normal is replaced by the semicircular law. So this not only suggests that there is a structure which comes out of the semicircular law in your mu f also. So, so somehow that helps you to get absolute continuity. Now, okay, what are some simple examples of this mu f? So one example is that, okay, so this is classically well known. You saw in the picture also that f is 1 means that it's a semicircular law. When say fxy is like a product rx into ry, then you can identify the mu f very explicitly as a free multiplicative convolution of two measures. So the first measure is, this is a semicircular law. And what is mu r? Mu r is the law of r of, so r of this weight, where weight w is the limiting law of the uniformly chosen vertex. So if you look at the law of this r of w, then you see that the semicircular law and mu of rw are kind of playing a role in identification. So for example, like, okay, if you forget, so the Chung Lu is kind of one of the examples where you can think of it as a rank 1 example uh, in this setting. So what about more general properties? So one of the properties we want to study is the moments of this mu f. And now to describe the moments, I will resort to what is called this homomorphism densities. And this relates a bit with what Clara was talking about, where you had to count subgraph counts. But this is a subgraph count in a more generalized setting. So suppose I'm given a function or a graphon. So graphon is nothing but a measurable function from this space to this space, which is symmetric. And you take f to be a finite graph. So this is sort of the copies of the graph you want to look into in your big graph. So it's a set of vertices and edges without loops. So I define a generalized homomorphism density from f to with this, and the notation is given by t of capital F, small f, and mu w. So how is this described? So this is an integral over the 0, 1 of this vertex set, and you look at the functions or the products of the functions at each of the edges. So at the end point of the edges, you look into this, and then you integrate with the way the measure you have. So let's look at one of these examples. Say my f is a graph which has two vertices with an edge. Then the TF is just given by fxy. So since I have only one edge, it's given by fxy and d mu xy, d mu x, and d mu wy. So if I have a graph like this, so where I have a square, then the function is, so here I look at, so this one is x1, x2, x2, x3, x3, x4. So say these are my four vertices here, and I'm looking at f of x1, x2, so this one, then f of x2, x3 is this one, and x3, x4 is this one, and x4, x1 is this one. So along the edges, I take the products and then integrate out this function. So if you give me any nice subgraph, I can write down these integrals. Now, these integrals are not just enough to describe the moments. What I need to know is also some kind of partitions. So, so let me also recall what these partitions are. So I look at examples of non-crossing partitions on partitions of 6. So it's best described through pictures. So this is a picture of a partition of 1 up to 6. So 1, 2 is in one block, 3, 4 is in one block, and 5, 6 is in one block. And for example, this is also a partition where 1 and 4 is in one block, 2 and 3 is in one block, and 5 and 6 is in one block. So these two are examples of non-crossing. And this is an example where a crossing happens in the sense that 1, 5 is in one block and 2, 6 is in another block, but this line crosses this line. So there is a crossing around here. So these are crossing partitions and these are non-crossing partitions. And it's classically well known that if you take 1 up to 2k and you are just looking at pair partitions, so pair partitions means each block are of exactly of size 2, just like these pictures. Then the number of non-crossing partitions is this number given by the Catalan numbers, which is given by CK. Another interesting fact is that every non-crossing pair partition of 2k gives rise to a rooted planar tree with k plus 1 vertices. So this is a fact I will use. Now, so I'm ready to state how the moments look like for mu f. So the moments of mu f, so if I look at the 2kth moments of mu f, then this is given by the graph homomorphisms of these trees or the rooted planar trees in my function f. So for example, if I'm looking at the second moment, I have already written because this is the only rooted planar tree you can get. So if I look at the fourth moment of my d mu f x, then I can write it in terms of, so this is 1 plus t of, this is another, which I can. So with this trees, so these have to be trees. So these are trees. So with these trees, I can exactly describe my moments of the limiting measure. And obviously, like the odd ones are 0. Okay. So given these measures, so this is the dense case. So let me go into the description of, so one nice thing is, okay, let me, before I go to the descriptions, for example, if f is 1, this quantity is precisely equal to 1. So the second moment is given by just ck, which is which are the moments of the semicircular law. So this is classically well known. And as you can see, the inhomogeneity kind of brings in contributions from each of the trees in an uneven way. So when you don't have homogeneity, you don't so when you have homogeneity, you don't see this contribution. When you have inhomogeneity, you start seeing these contributions to each of these planar rooted trees in this with this t function. Another fact is, although this is not completely in the dense case, these homomorphism densities are very crucial in the graphon theory, which is only used in the dense case. Now you see them appearing in general in the moments also, because somehow these are basic building blocks in the dense graph theory, and they play a crucial role later also. Okay, to describe the sparse case, it's a bit more complicated. So here I take the notion from, so I should have mentioned this. So this is a notion by OWPS and Priyanka Sen, which is they call as a simple symmetric partition. So here I take a partition uh, of k, 1 up to k, which I call as v1, v2, vk. So these are all blocks. So I call them simple symmetric partition if between any two successive elements of any block, there are even number of elements from any other block. Okay, so this is a complicated definition. So let me just explain with this example. So 1, 2, 5, 6. So this is a nice example. So 3, 4, 7, 8. Now, what happens So here, one thing to note is 0, I count it as even number. So between 1 and 2, there are 0 elements from other block. So it is a valid thing. Between 2 and 5, I always have 3 and 4. So I have two elements which can go in between 2 and 5. Between 5 and 6, I have again 0. Between 3 and 4, again I have 0. Between 4 and 7, I count this inside. So I have two elements between 4 and 7. And between 7 and 8, I again have 0. So this is an example of a simple symmetric partition. In fact, one can show that all non-crossing partitions kind of fall as a simple symmetric partition. And there are also examples of non-simple symmetric partitions. Now, given a simple symmetric partition, what you can do is you can visualize this partition as a permutation. So what I mean is, for example, if I consider this, so 1 goes to 2, 2 goes to 5, okay, here 3 goes to 4, 4 goes to 7, 5 goes to 6, 6 goes to 1, 7 goes to 8, and 8 goes to 3. So I can visualize this as a permutation. Now, once I visualize this as a permutation, say for example, this was as a permutation, I take a permutation which is just a right circular shift. So 1 going to 2, 2 going to 3, 3 going to 4, like this, say m going to 1. And I multiply these two permutations, I get a new partition or a permutation here also, which is looks like this. What I do is I make a graph out of them. I put them on the vertices here. So I make these vertices to be, uh, so I make three vertices like this, V1, V2, V3, and I make edges by traveling along these, 1 going to 2. So I do a travel along these vertices. So I travel 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, then 5 goes to 6, 6 goes to 7, 7 goes to 8, and 8 goes to 1. And I remove the multiple edges. So I make this and remove multiple edges. So if I remove multiple edges, I create a graph like this. Now, if I take a partition which is not simple symmetric, I see the graphs are not like trees, they have loops. So this is the main fact. And if I take a simple symmetric partition, these are all trees. Now, that gives you a kind of the first basic thing, that if I look at the moments of the in the sparse case, so there is a part which comes from the dense case. So this was the dense or the intermediate regime moments. Then you start getting more factors within. So the first factor is the alpha inverse. And then you look at the sum over all partitions in the simple symmetric fashion, which are non-crossing. And you look at the copy of this graph in F. So these are these homomorphism densities. And slowly you go on. So the next power is alpha minus 2, and so on. Then you have alpha minus k minus 1 with these kind of factors. So what you see is that you get a polynomial which looks like A0 plus alpha inverse A1 plus alpha minus 2 A2, like this. And it's a finite polynomial. But what is interesting is that these moments are exactly equal to the dense case plus some OK times 1 by alpha. Now, this is one way of comparing the distance, although we could not get the optimal results because we don't know how to exactly count these. So these are some partitions. They could be represented as some kind of colored trees, but we don't know how to do this. Okay, so just finally few properties of this mu f alpha when f has unbounded support. Uh, So mu of f alpha has unbounded support. And we also know that if the local weak limit is a unimodular Galton-Watson tree, then you have an absolutely continuous part in the spectrum. This was proved by Aras and Bogdanov. There are atoms, this was shown by Sales, that atoms are given by the totally real algebraic integers. What are these? These are some roots of monic polynomials with integer coefficients. Uh, what is not known is that whether this measure has a continuous singular component. So this, I believe, when the last I checked, that there was no result which claimed or refuted this claim in any way, that that whether this is not there or this is there. Okay, so in the last sort of, I always take my time. In the last 5 minutes, I'll just briefly give you what happens with the Stieltjes transform of this mu f. So the Stieltjes transform of mu f is defined as an integral of 1 by z minus f mu f dx. And you can write this as uh, an integral of an analytic function in two variables. So one is a complex variable here, z. Another is a real variable, 0 to infinity. And this satisfies an analytic functional equation like this. 1 by hzx is equal to z minus integral of this quantity. Now, this is sort of a recursive analytic equation, which kind of has a unique solution, and you can write down the Stieltjes transform using this. So what happens is, I'll not go into the details, but I'll skip this. So what we could show in the recent work is that the Stieltjes transform in the sparse case converges to this mu f alpha or mu alpha f. I use it interchangeably, of the Stieltjes transform of this measure, and the limiting measure has a complicated form here. And I don't describe you this phi star, and phi star comes actually from a fixed point of an operator on a Banach space, on a nice Banach space. It comes as a fixed point of the nice Banach space. Now, you could explicitly describe this, and from there you can show that if you again let alpha make it large, then the Stieltjes transform converges to mu f, S of mu f. So again, this is the sparse case to the dense case. Now, the thing we were missing here, that what is the error in the convergence? Because there is this nice metric which you can define on the space of probability measures. So you take these two measures, you can compare the Stieltjes transform of the dense case minus the Stieltjes transform of the Stieltjes transform of the dense case with the sparse case for all imaginary z greater than 2, so bounded away from 0. So if you can get a nice rate on this, this was our target, that we could try to achieve uh, the rate of convergence or the difference of this, then you would possibly get a rate of convergence. And again, it seems we are a bit away from the optimal rate, and it seems not a very easy. In fact, uh, there are many critical points so we have to do a lot of swapping of integrals, differentiation, Bessel functions, and everything. And there are some places where things absolutely go crazy. You could do it like phases, or somewhere that you could swap things. Things do work well, but there are places where you have a infinity minus infinity kind of a thing, and then you are really stuck at some point. So as I promised you, there is this final thing I wanted to comment about the weights being random. So this is one nice result. We are doing more work on this. So if you look at the torus, so my vertex set is now a torus, d-dimensional torus, or a discrete torus. In dimension 1, it's just points on the circle, which are uniformly spaced. And I have weights which come from power law distribution, as Clara was doing. So it's just Pareto distribution with tau greater than 2. so having finite mean. And conditionally on these weights, I assume that they are connected by 1 minus exponential of wx wy divided by the distance. So this is the geometric factor which plays a crucial role, x minus y power alpha. You could also take, for example, this wy by norm of x minus y power alpha minimum 1. Or there are more forms of this, but the important part is that distance between x and y also comes in. So this geometric factor comes in. Now, here I call this the dense setting. When this parameter alpha is less than the dimension, then you can show the empirical spectral distribution with the scaling. C is some constant. I'm not saying it immediately. It comes from zeta functions. If you scale it by n to the power d minus alpha, then you see that you have mu semicircular law with this free convolution with mu w. And this is not a compactly supported measure. This is an unbounded measure because mu w is a power law. It's not like the previous case where you had unbounded measure. But we could prove this. The more harder question is what happens when alpha is greater than d, because the scale-free percolation on a torus locally weakly converges to a scale-free percolation on ZD. And scale-free percolation on ZD is an equally difficult object in terms of understanding the adjacency matrix. So it's a very complicated object. It's just not described by Galton-Watson trees. It's much more than that. So here what we'll resort is the techniques which I skipped in the Stelios transform part. So we'll resort to those techniques to prove them. And so, yes, thank you for listening to this. And if you have any questions, please feel free to ask.
All right. Thanks a lot, Rajat. All right. We have time for a few questions. If anybody has it, you can raise your hand. Okay, Nelly. Nelly, do you have a question?
I have a stupid question, if that's okay.
Yes, they are not
fine,
never
yes.
they are never stupid. I know.
No, that will be stupid, I promise. Okay, so okay.